Hello, my name is Ben Snively. I'm a specialist solutions architect in data and analytics, and thank you again for joining us. Data warehousing has been around for quite some time. What it really deals with is handling relational data. That relational data could be at a gigabyte scale, but also range all the way up into the cloud to the multi-petabyte scale. And the cloud really enables you to very elastically scale this using services like Redshift, which we're going to talk about shortly. And a lot of times customers are using this to be able to do operational reporting of various data sets coming from various systems. That could be transactional databases, ERP systems, various line of business applications. But when you're talking about data warehousing, oftentimes you're talking about what's called schema defined prior to data loading, or schema on write. And what that means is as you're running your data warehouse, before you load your data into your data warehouse, you first load it into a schema, which is defined in the warehouse as you're loading the data or before you're loading the data. And within AWS, we have a really fantastic data warehouse called Amazon Redshift. It's very, very powerful. It allows you to massively scale and parallel up to petabyte range and very easily scale with a few clicks as you need to. It's fully managed, so you really could focus on designing your database schema and really focusing on your business applications and your ETLs within your data warehouse. There's multiple flavors, and they really fall into two high-level categories. The first is dense storage, which is really HDD-based, and the other is dense compute, which is SSD-based, and really lets you cater your data warehouse based on different types of platforms depending on what your use case calls for. And the really powerful aspect is it's able to be start at a very, very low cost bracket. You could actually have a full functioning data warehouse for, really around $1,000 per terabyte per year, which for data warehousing is really, really amazing. And this all really drives being able to run very, very fast analytical workloads, being able to do it very easily, so very easy to use, and making it less expensive to run, being able to elastically scale, leverage what you need, and then grow as your demands, either grow or shrink as your demands call for it. One fantastic customer that's leveraging Redshift today is Nasdaq. Nasdaq is using various AWS services, but within Redshift, they're bringing in over 5.5 billion rows every day to be able to really analyze financial trade information. And they really want to be able to do that over a very large footprint of data. And Redshift has really given them the power to do that. In fact, at times they even peak to about 14 billion rows ingested per day within the Redshift cluster. So they're one example of financial industry. And the reason why I like to mention this is very heavily regulated, very, very secure industry. Another one is within healthcare. So Philips is actually leveraging Amazon Redshift to be able to load millions of records and run complex healthcare analytics within the Redshift cluster. And they're able to do that within less than a second using Cloudbeam Eternity, one of our ETL partners that we're going to be talking about later. So before we dive into the technical details, I want to give a couple example use cases of how customers are using it today within AWS. So diving more into Amazon Redshift, the first is it's very, very fast and easy to use. We're going to show within a few clicks how you could launch a cluster, how you could configure it, how you could extend that cluster into your data lake, and what that means to extend it within your data lake. And it's very, very scalable. So as you launch your clusters and as you're using your data lake, it's all based on a consumption model and growing based on your needs or shrinking based on your needs. And security, number one priority across all these services. So auditing, encryption, multiple ways of handling encryption keys, all built into the service. So diving a little bit into the ease of use, and we're really going to go over some high-level aspects of Redshift, but then really talk a lot about best practices and how to design your data warehouse. But it's very easy to provision your warehouse in minutes. It's fully managed, so it's automatic. It has automatic patching, very easy to load SQL, and security is built in all the way from the ground up. So some example customers of really quoting how fast the Amazon Redshift really is. So a wide number of examples, but just to call out a couple. So One is Pinterest. So they're leveraging Amazon Redshift to be able to generate some queries over their data set. They migrated over a Hive Hadoop implementation and saw orders of magnitude 50 to 100 times speed up over what they were doing using Hive for their original queries. Another example is Redfin. They actually were quoted saying it's ridiculously fast being able to run their analytics over some of their other implementations. So many customers are finding it very, very easy to launch the clusters, but with some very simple tuning, able to get very, very high performance out of their cluster. Amazon Redshift is really built on an ecosystem of AWS services, such as AWS Glue to be able to do ETL, as well as QuickSight, which we're going to talk about later, but also an ecosystem of partners. So within Redshift, you could use a very wide number of tools as a BI platform on top of your Redshift cluster. Amazon QuickSight is our BI tool. You could use Looker, Tableau, Pentaho, many other tools that are very easily consumers of your data warehouse within AWS. And the reason why that is Amazon Redshift uses very, very standard JDBC or ODBC drivers to be able to very easily bring those data warehouse products into the platform and query over your analytical data sets. Just talking a little bit about some additional partners, we talked about the business intelligence partners on the right-hand side. There's a wide number of system integrators that will really help you get started and launch your cluster, help you maintain it, follow the best practices of tuning your cluster. But also there's data integration partners. So these are partners like Cloudbeat with Tunity, Informatica, Pentaho, Talend, many others that really focus on data integration. So how do you get your data from your different data sets, which could be within the cloud or on premises, and how do you load it effectively into your data lake and your data warehouse? So, we have some really fantastic services here, but we also have a really great partner ecosystem that customers could leverage within the Redshift and data lake platform. Here's another example of how to get your data into your Amazon Redshift cluster. The database migration service. It's really, really great at being able to migrate both homogeneous databases, meaning I have a SQL Server or Oracle or a database running on premises and I want to move it in and out of the cloud easily. But it also lets you do replatforming or heterogeneous migrations. So what if I have my data in Teradata or an Oracle database? I'm using it as a data warehouse and I want to get it easily into my Redshift cluster. Database migration service in conjunction with a schema conversion tool really allows you to set up migrations into your Redshift cluster very, very easily. It is able to identify things that are lift and shifts. So how do you want to restructure your schema? But it will also identify elements that may not easily be migrated. So if there's certain stored procedures or how do you want a sequence handled in one platform that another platform maybe doesn't have sequences. So it does the simple things really, really well, but it will also identify what it can't migrate and give you a very nice action plan of this is what I should look at when I'm considering this migration. And because of all this, it's very, very fast, easy to use, very, very secure. We're really seeing it across a wide number of industries and mission critical workloads. We already talked about NASDAQ in the financial industry, FINRA, who regulates trade information for security brokers, also is a heavy user of Redshift. But we see it in the retail business, the healthcare business, and public sector. For example, Center for Medicare and Medicaid is a very heavy user of Redshift. So really across all the industries, we're seeing a wide adoption of Redshift as their data warehouse. So let's talk a little bit about Redshift and then how it integrates with your data lake. And then next we'll actually dive into a demonstration after that. Some best practices when you're looking at your Redshift cluster. The first is Redshift stores things as a column-oriented storage. What that means is if I'm storing my data, and if I have this data that has 3 columns in it representing in this table, all of the data for one column is stored together. And the reason why this is very, very optimal is when you're doing deep analytical queries, rather than picking all the attributes of one row, oftentimes you're querying over many, many rows, often all of them, doing various aggregations, analytics, that sort of thing across all the data, which really optimizes the way the query happens under the covers. The other best practice, or the other thing to look at, is compression. So there's compression built in, but you could also select from a wide number of compression algorithms when you're compressing your data. And the nice thing about this is since the data is stored column-oriented, you could actually have different compression algorithms based on the column or the type of data. Because the way you might store an integer might be different than the way you store a string, which might be different than a date. So this really lets you optimize and pick the right compression algorithm or codec based on the type of data that you're going to be querying over. So it really makes it very, very optimal when it comes to I/O and reduces the storage requirements within your Redshift cluster. The other thing to consider when you're looking at running your Redshift data warehouse is how to handle the sort keys. What sort keys really do is it really lets you physically sort your data on disk across your nodes. So if we have this example data table that has these 3 columns, if I specify a sort key based on the date and location, on disk we could actually sort the information. And what this allows us to do is very quickly jump to different blocks that have the data or may not have the data based on the constraints of the where clause. So here we could actually see 2 locations with the same date. Since we actually said date and location, it's actually sorted in date order. And this is how it show up actually on disk. And what this allows us to do is really set up Bloom filters or zone maps based on the sorting. So if I don't really have any sorted data, if I actually do a query and I query for a particular date, it might have to look over all these blocks of data because it's not sorted by date and it knows the min and max value for date. So it's going to scan it over a very large amount of data, almost all the blocks of data. If we actually sort by date within our sort fields, what it allows us to do is very quickly, whenever you're querying based on date, only jump to the blocks that have those dates in it and really reduces the amount of work or the amount of I/O that the entire cluster has to do. So in addition to the compression and understanding the distribution, sorting is a really good best practice when you're looking at your Redshift cluster. So in conjunction with that, there's a concept of slices. And you can really think of a slice as a compute unit within the cluster itself or within the node. When you're launching a Redshift cluster, you could specify n number of nodes, and each node will actually have somewhere between 2 and 32 slices within that node. And that is actually a unit of work that allows you to both parallelize your data across the cluster, but it also, as you're doing queries, it lets the queries operate in parallel and get the answer to you much, much quicker. And the way that the data is distributed across the cluster is based on the slices within the cluster itself. And there's really 3 different ways of distributing your data when you're looking at optimizing your Redshift cluster. The first is key-based distribution. And this really lets you put all the data with the same key on the same slice and on the same node. This is really used if you have, let's say you have 2 very, very large tables and you are oftentimes joining those tables together. If you actually set the key to be that join field for both of those tables, it really reduces the network I/O because one slice will always have both ends of the join criteria as it's joining the data. Something to be cognizant of, you do want a high coordinality for the key values because if I actually only have 2 values for key, I could at most leverage 2 slices. So you do want to pick a key column that has a high coordinality or high number of values so you get an even distribution across your slices. The other option is really all. This is heavily used for dimensional data. Maybe you have under 1 million or a few million rows, and you really want a copy of that data across all the nodes. That way, if oftentimes they'll be joined across many of the different data sets, each node will actually have its local copy. And that goes on the first slice of each node. And if either of those don't apply, really the default or the go-to is that even round-robin distribution. And this really ensures the parallelism and makes sure that all the slices could work on the query at once. Here's some of the best practices that we briefly talked about, but really the DISTSTYLE of key is used to really optimize join performance, inserts, group bys, by really having all the data local on that slice or on that node. All is really used a lot of times if you want to join with dimensional tables. So if you have less than a few million, it lists 3 million here. All is a really good way of having a copy of that data, that dimensional data for all your joins across all your nodes. And then if neither of those apply, go ahead and kind of default to even as a good fail-safe. We're not going to talk a lot in detail in this webinar about this, but there's some really great administration scripts on our GitHub site on AWS Labs, which will let you go in and see your data skewness and see how much data is on one node versus the other. And this slightly calls it out in this presentation here, but if you have a high skewness, you probably want to consider looking at a different distribution model. Related to the slices and performance of the slices is really how quickly can you ingest data into your Redshift cluster. And that's oftentimes done best practice through a copy statement. And what a copy statement really does is it goes through a leader node, which accepts all the JDBC and ODBC queries, and then goes down to all the compute nodes and tells the compute nodes to load the data in parallel. And some best practices when you consider what that flow looks like. The first is each slice will actually ingest some of the input files based on your copy statement. So rather than having one giant input file, which will only leverage one slice, really ideally you would actually have a large number of input files so that all the slices could work in parallel. And you really want these input files to be relatively the same size. You don't want one input file that's very, very large while all the others are tiny. And best practice is, between 1 meg and 1 gig for each of the delimited files. So this will really speed up when you're loading your Redshift cluster warehouse. Last couple items, and then we're going to dive into how this integrates with your data lake, is the node types. What type of node? There's really two high-level node types that we talked about briefly at the beginning. The dense compute, which has solid state, and the dense storage. And each of these have different storage to CPU and slice ratios. So if you need to store more data, you could actually start with dense storage. If you really need more horsepower, more slices, more compute, you could actually shift it to more of a dense compute model. So how does this all fit into data lakes? So data lakes are a little different than a traditional data warehouse or database, where with the data lake, you're really storing the data at rest, oftentimes in a raw form. So your data could be coming in Parquet, CSV, log formats, Avro, many different formats into your data lake. And then, oftentimes what happens is rather than defining your schema up front, like a traditional data warehouse or something like Redshift, you actually define your schema after the fact, schema on read. And what Redshift Spectrum allows you to do is it really lets you combine both the Redshift data in your data warehouse with your schema on read data within your S3 data lake. And it lets you do this really, really effectively. And we're going to give a couple demonstrations of this here shortly. But before we do, a little bit more about data lakes. One of the, a few of the things to definitely consider when you're looking at your data lake. The first is, being able to store any type of data. When you're looking at storing your data, oftentimes It's really good to store in some sort of standard format. So if it's CSV, JSON, Parquet, some industry standard format that allows many different analytical tools to use that data. It of course needs to be secure and prevent unauthorized access. One really important aspect is really being able to search and discover your data. It really makes the difference between a data lake and a data swamp. And what that is being able to find your data and catalog what data you have within your data lake. And within the data lake, it's really heavily decoupling the compute from the storage. That way, it really lets you independently scale those in a high-performant way. So as you bring more stuff into your data lake, you don't necessarily have to spin up more CPUs unless you need that in order to analyze new data. So the way this really works is data lakes are really extending traditional data warehouses. Oftentimes we have customers, for example, FINRA we were talking about earlier, that are very heavily using both AWS S3 data lakes or data lakes built on Amazon S3, as well as Redshift together in their analytical solution. And this really lets you scale up to exabytes if you need to. So if you need to be able to have your business intelligence users using your data warehouse, but also do queries against your data lake, it really lets you scale very, very high scale. It allows you to run diverse analytics. So one of the key things about data lakes is future-proofing to the type of analytic you want to run. So you might want to run machine learning, deep learning, neural networks, real-time analytics, being able to have a wide number of tools against your data within the data lake. So how does Redshift Spectrum really do this? It really is built into the Redshift cluster, and we'll show you live, stepping through kind of some of the process to be able to show how to set up the external schema within talking to your data lake and start querying your data in place in S3. Under the covers, this is how it works. So Redshift Spectrum is actually an extension on top of Redshift. And what it allows you to do is really delegate work down to a different layer of compute nodes, which is actually interacting with your data lake on S3. So from the querier's perspective, all they see is an external table here. So they still are able to issue queries against JDBC and ODBC through that leader node. That leader node recognizes which columns and tables are within Redshift Spectrum in your data lake. And remember, these are columns that were defined after the data was stored schema on read. So the data could exist in S3 prior to the table definition within Redshift Spectrum. And then what it does is at the compute layer, it actually delegates that work down to the Redshift Spectrum layer. Each slice will actually query up to 10 parallel nodes or compute units within the Spectrum layer to then be able to query your data as it rests on S3. And the really powerful aspect of this is you can actually join data that is both on your Redshift cluster loaded on the storage within your cluster with data that might be at rest within your data lake. So if you're bringing in new data sets into your data lake, or if you want to have different hot and cold data sets on S3 versus loaded within your Redshift cluster, you can really do that really effectively and have one central query mechanism through that leader node using Redshift and Redshift Spectrum against your data lake. And one of the best practices and one very common way of doing this is actually leveraging AWS Glue. AWS Glue allows you to create a common data catalog. It does this using crawlers. We're going to demonstrate here in a moment how the crawlers work. But within S3, you could have a wide number of data sources. The crawlers will discover that data and create that catalog for you. And then through Redshift Spectrum, as well as a wide number of other tools, again, you want to future-proof, so it's good to have a wide number of tools that interact with your catalog and your data lake. You could bring that in and do queries. We're going to focus on this bottom flow here of how to use the catalog with Redshift Spectrum because we're extending our data warehouse into our data lake, and then how to use our BI tools to be able to query the different data sets there. Before we do that, another example of a customer doing exactly this is Nuviad. So they're leveraging Redshift Spectrum along with Redshift and Glue to be able to really bring in data much faster than they were able to do before. So before, they would actually have to take minutes to be able to generate certain reports and get very, very real-time information into their dashboards. Now they're able to do it very, very quickly within seconds. They get their data because it's schema on read. As soon as it lands in S3, if they query that data, it's going to return that data, and very, very fast delivery using open file formats within the ecosystem. So very easy to put these pieces together. You could start small with Redshift, bring in Redshift Spectrum, you could bring in Glue, and then start adding these pieces as you need them based on your use case. So very, very powerful to do that. So lastly, before the demo, we're actually going to step through what this looks like under the covers. So this is, this is an example query. And one of the things you'll notice is there's actually two tables being queried, this S3 dot, as well as this products. And this S3 dot could have really been named to anything. We just named that in this example query to represent external schema, represented the schema on S3. And you'll notice it's very easy just to treat these as two different tables, even though this is a table loaded on the cluster, this is a table in the data warehouse, and then you could just query kind of like usual against your data sets. And very easy to do aggregations, that sort of thing. To show a more complex example, you could easily take your data in S3 and join it across multiple tables within your data warehouse. Or you could actually leverage multiple tables in S3 to be able to then do very complex queries. And this is really where a lot of the power of Redshift Spectrum shines, where it's able to do predicate pushdown when it can. It's able to aggregate at the compute layer against data that already exists in the warehouse and do very, very complex queries with the cluster. So we're going to dive into the demonstration next. So we're going to start with a data warehouse that we have running and then show how you could extend that data warehouse into your data lake, stepping through some of the process. So we're really going to start off with this cluster that we have running here. So this is a 4-node cluster. If I want to simply resize it, it's super easy to do that. I could go in here and I could do this programmatically as well. And I could go in and change the size of my cluster. I could still query my cluster as it's changed in the size. So it's very easy to start with a small cluster, grow your cluster or shrink it as you need to. Take automatic snapshots of the cluster. Very easy to stand up this data warehouse. But I have this warehouse running. So let's say I want to start looking and analyzing that data. First, what I'm going to show is I'm going to show a SQL workbench here. We're going to actually just connect to the SQL workbench. I'm going to maximize it here. And this is just showing one of the ways to connect to your data warehouse. So it's connecting right here. And what I could do here is I could actually look at all the public schema. So this doesn't necessarily mean public to the world, but a schema named public here. And these are all tables loaded on my warehouse. So I could select this table. I could start interacting with it. I happen to be using SQL Workbench, but if your DBAs and data warehouse experts use different tools, as long as they integrate nicely with JDBC or ODBC, very easy to look at your data, manage it, see all the data on your cluster, that sort of thing. And just to show what this data looks like, I'm going to do a quick query. This is looking at venue data. We could see various event names, wallflowers, return to forever, various events here, when the event was, and the different categories. So we haven't really extended into our data lake yet. Everything that I've shown so far has been within the data warehouse already loaded using those copy statements that we talked about earlier. What if I wanted to look at some of the data in my data lake? What I have is I have this transportation schema. And one of the things that we'll first notice is you'll notice a type called external table. This is actually external schema using a external schema in order to talk to the data in the data lake. Just to show another way of interacting with this, and we'll set up another one of those external schemas in a moment, is I'm going to just connect through pSQL this time. And And the reason I wanted to show this is just, there's multiple different ways of interacting with the Redshift cluster. You could use the right tool for the right job. So if your DBAs and whoever you're working with really likes to use certain tools, it's very, very easy through that ecosystem to use different tools for different jobs. Let me just turn on timing here so you can see all the times that it takes to run some of these queries. And the first thing that we're going to do is we're actually going to look at the various tables on here. So again, you'll see the tables that we just looked at through SQL Workbench. If I look at the various table, I could actually see the event table here. So this is all the details about the event table. Let's take a look at the schemas. So these are the schemas here. You'll notice that public schema as well as our transportation schema, which is an external schema into our data lake using Redshift Spectrum. And what we're going to do is we're actually going to create another schema here called data lake. And we're going to do that by just issuing this query here. And this is actually going to create a external schema within our system. So now we see actually 3 schemas, right? We see a new one called data lake. And this is actually using the IAM role to be able to talk to that data lake. And we're using the Glue data catalog to be able to link it to the Glue data catalog's definition of all the schema on read in our data lake called the namespace data lake. And we'll step through what that looks like in a moment. But before we do that, I want to issue this other query showing all the external schemas. So here we actually see 2 external schemas, New York City taxi and flight delays. And also where the data lives on S3. So these are data sets that if we query these, it's actually going to query the data as it rests on S3. We're not loading the data directly into Redshift when we're leveraging these external schemas. So let's take a look within Glue here. So if I go ahead and switch over to Glue, one of the things that we'll notice is this data lake schema here has that New York City taxi data. But what we could do is we could leverage crawlers. These crawlers allow us to run over data sets within S3 and discover new data. So when we configure a crawler, you'll notice it's actually crawling a very generic bucket name. And what it's going to do is it's going to find all the data that is within that location. And it's going to categorize that data. So some data set within this location is CSV, some is JSON, some is Parquet. There's many different data formats and data types within this location. And what you'll notice right away is if I search for a data lake, a very large number of tables. These are schema on read tables, so these data sets already exist. And it just discovered all of this data sets when I ran that crawler. For example, if I go ahead and look in the Twitter data, I could see that this is JSON data, and it found very nested elements within here. So if I go ahead and select this struct, it automatically discovered within the JSON this very, very deeply nested data structure for me that I could very easily query over using Redshift Spectrum, using Athena, using EMR, which is Elastic MapReduce, which is really the Spark and Hadoop ecosystem as a service. But to show how we're extending our data warehouse into the data lake here, what we're going to do is we're actually going to go back here and we're going to issue this query. And one of the things you'll notice is it knows about all these kind of quote tables. These are schema on read tables within S3, and it knows that through that Redshift Spectrum and the Glue integration. So very easy to put these things together and extend that into, extend your warehouse into that data lake. So let's start querying some of this data. So next, I'm actually going to show the partitioning information for one of these data sets. So what we could do is within Redshift, we could query for the partitioning information. In data lakes, it's a really good best practice to look at like column-oriented storage and partitioning of data. And what that allows you to do is if you structure your partitions a certain way, if I actually queried for all the taxi information about yellow taxis, or for the month January, it automatically knows which, it does partition elimination at query time based on the query parameters. So it really lets you reduce the amount of work each query has to do based on those query criteria. And it automatically knows you don't have to necessarily specify these in order. You could actually just specify a particular year or month or types of taxi. I'm only showing the first 15 partitions here, but there's many, many more partitions in this particular data set. And AWS Glue allows you to very easily structure your data in that format using our ETL services. So definitely something to look at if that's something you're looking at doing. The other thing that I want to show here is how you start querying the data. So you'll notice that this actually is querying a data lake.New York City taxi data. And when we actually query this data, it's actively going out to S3 and querying the data. And you'll notice that only took about 3 seconds to query because I have timing turned on. So that was doing partition elimination because I specified year 2016 and calculating the average cost, the average distance, the average cost per mile for all the different taxi types within 2016. And none of this data was actually loaded into the data warehouse when I was doing this query, but I did structure it in an optimal way. So I did partition the data and I did put it in Parquet format. You don't have to do that, but by doing that, it really speeds up some of those queries. The other query I want to show is how you can start looking at the performance of your Redshift Spectrum cluster. And what you could do is you could very easily start looking at how much data am I scanning for various queries out of S3. Am I effectively using partition elimination? Am I using all the slices to parallelize my workload? So there's a set of views that really allow you to inspect per query how effectively you're interacting with your data lake. We're not going to step through each of those views, but definitely take a look at within our documentation some of these different views to be able to answer those common questions as you're integrating your data lake and your data warehouse. Last couple things I want to show here is how you can start integrating both the data stored within the Redshift cluster as well as the data that's in Redshift Spectrum, or I should say your data lake through Redshift Spectrum. So this next query here, again, you can see it returns quite fast. This is a new table that we just discovered using the crawlers. That data lake.sales table didn't exist until that crawler ran. And what you'll notice is, we're actually querying a combination of the data lake tables, these schema on read tables, with the event table that's already loaded in the Redshift cluster. And from the person writing the query's perspective, all they have to do is reference the external schema. They see what table, what columns exist for each of those tables, and they could easily join it with the different data sets there. One last query that I'll show here, and then we'll dive into a little bit more on how this integrates with BI tools, is this last query is really joining a large number of tables together. So it actually adds another table. It's doing a 99th percentile, and again, very easy to go and write this query, and then show the top concerts, the categories, the events, the total price in a very simple query to execute. So you might be asking, how can this start integrating with BI tools, and what does that experience look like? So I was going to spend last few minutes stepping through that. So I happen to be showing QuickSight here. So we're going to be launching QuickSight. QuickSight is our BI tool. We also have really great partners that integrate with Redshift Spectrum. QuickSight is very, very easy for folks to get started with, though. So I'm actually going to switch over to the Oregon region because that happens to be where I'm running my Redshift cluster. And I'm going to go to this analysis, and what this analysis is doing is analyzing that same data. And this, I happen to select, just very easily what columns I want to visualize across these displays. This is showing, per venue, which are the most common venues, as well as a timeline here. And the way I was able to build this, really within a couple minutes, is when you go to manage data, it's very easy to go in here and set up the data source. And even if you're joining the tables together, you can specify what the join criteria is across your tables within Redshift. You could prepare this data set, and then everyone could use this data set very, very easily when they're building dashboards and analysis within the tool. But what I could also do is I could actually go in here and I could actually go in and set up, so that I am also doing a query across the tables. So if I wanted to actually create a new data set using Redshift Spectrum, I could go in here and do that just by selecting Redshift. I could say create data set. And one of the things you'll notice is, I could very easily select that data lake. These are all the data sets out of the Redshift Spectrum. I could actually select the data that's within the cluster itself. But what I could also do is I could actually go in here and say, I want to actually go in and use a SQL statement. And maybe I want to do that same query I was doing earlier. And this is actually joining those data sets together. So it's very, very easy to go in and do a custom query that's joining the different data sets from both Redshift and Redshift Spectrum within your BI tools within, we're showing QuickSight here. So, so what we're demoing there is just a lot of the different pieces of how to set up your data lake extension from your Redshift cluster using Redshift Spectrum, how to start analyzing the integration between your data lake and your data warehouse by using those views, and then start joining the data sets together. A few last recommendations I'd just like to give folks before we answer questions. The first is always look to optimize your data lake and your data warehouse. One of the ways of doing that is you could actually push those scan-intensive workloads down to the Redshift layer and leverage that Spectrum compute layer to really offload a lot of the scan-intensive works, because when it's actually at the Redshift Spectrum layer, you're not consuming the compute resources within your nodes within your compute cluster. The other is when you're looking at your data lake to really optimize for that data lake. So leveraging column-oriented storage, partitioning your data, also knowing the level of parallelism for your Redshift cluster. So if you test Redshift Spectrum out and you have a large number of compute nodes, you probably have a very high level of parallelism. But if you happen to launch Redshift with one compute node, maybe it's a dense storage, a very small one, you might actually only have 2 slices for an example. At most, you'd actually have a 20 parallelism down to that Spectrum layer. So the amount of parallelism at the Spectrum layer is directly relational to how many slices and how big your compute layer is. And you could also leverage a lot of best practices of predicate pushdown. For example, if you leverage group by statements within your select statement rather than doing distincts and some other best practices. And we have some really good blog posts that talks about the top best practices of optimizing your data lake, your Redshift and Redshift Spectrum within the AWS Big Data blog. So the last thing I want to mention is this white paper talking about data lakes on AWS. It's a really great white paper talking about how to set all this up within AWS, set up your data lake, how to make it future-proof, leveraging things like S3 and AWS Glue within the ecosystem. So wanted to thank you. We'll stick around and answer a few questions, and thank you again for attending our webinar.